And let me also share my screen. All right. Okay, I take it you can see my screen, right?
Yes.
Okay, good. All right. So we're going to continue our discussion, and actually we're going to complete chapter 3 and move on to chapter 4 today. So one of the last things we're going to discuss in this chapter is the concept of dilutions. Now, as stated here, dilution is a simple process of increasing the volume of a solvent in a solution by adding more of the solvent to it. And this is something that is routinely done in labs all over, not only in chemistry labs, but other labs where solutions are used. And this is because very often, sometimes an experiment would call for a solution of a particular concentration, which we may not have at hand, but we can have a more concentrated solution, and therefore we can dilute it to the level that we need in order to conduct the experiment. All right, so this is something that happens every day. And in fact, for those of you enrolled in my lab, we'll be doing an exercise based on this very topic. So we are actually dealing with this topic at a very timely juncture of this course. Okay, key thing you need to remember when it comes to dilution is right here. The addition of the solvent does not change the amount of solute, all right, in the solution. Very important. So basically all you're doing is increasing the volume by adding your solvent, but you're not changing in any way the amount of solute. And because there's an inverse relationship between the concentration and the solute, and the volume, I'm sorry, if you increase this, right, if that increases, if the volume increases, that means that correspondingly, the concentration decreases if the moles does not change. Does not change, all right? So that's basically the principle underlying the whole dilution idea, all right? So, a minute here. Just to give you, as I said before, those of you enrolled in the lab will be doing this today, but basically what you're doing in dilution is shown here in these pictures. So here we have a copper 2 sulfate solution, and I'm not sure what the concentration is. The label is so small that I can't make out the handwriting or the typing on the label. But basically, this would be a relatively concentrated solution of copper 2 sulfate. And what this person did was basically withdraw 50 mils of the solution here into this piece of glassware known as a volumetric pipet. A volumetric pipet is basically a glassware which is used to measure volumes of a particular, one particular volume. So they come in different sizes. You can have, I think the smallest one I've seen is a 5 mil pipet, and they can go up to, I think the largest I've seen is a 50 mil pipet, all right? So in this case, the person is pulling up 50 mils of the copper 2 sulfate into the pipette here and transferring it to the volumetric flask, which is what we have here, all right? The volumetric flask also is made very accurately. There's a mark, which you can't see, but there's a mark that is etched on the stem of the volumetric flask, which is a particular volume. So again, these come in different sizes. You can have 5, 10, 25 mil, 50 mil, 100 mil. I think the largest I've seen is like a 2-liter volumetric flask, all right? And then after the person transfers the copper 2 sulfate to the flask, then to dilute it, the person would add water up to the mark, and therefore you'll end up with the more dilute solution. So that's basically what dilution is all about, all right, in practice. Now, the next slide, oh, before we move on to the next slide. So again, the key thing you need to remember is that all you're doing to the solution is increasing the volume, all right? You're not changing the amount of solutes, as stated here. it's the same number of molecules present, or in this case, ions present before and after the dilution, all right? However, because you're adding the volume or increasing the volume, then the resulting solution will be less concentrated, or you could say more dilute. So here are a couple of examples of dilution type problems. And the first of which is if 45 mils of water added to 250 mils of 0.75 m potassium sulfate, what would be the molarity of the diluted solution? Now, one thing I should have mentioned, which I'm going to mention here, is that the equation that is used for dilution, and this is something that you should have met before in your high school or introductory chemistry, the equation that you'd use for this type of problem is C1 V1 is equal to C2 V2, all right? So C1 and V1 would be the initial values of concentration and volume for the solution, and then C2 and V2 would be the final concentration and volume after dilution, all right? So the initial would be C1 V1 for concentration and volume respectively, and then after dilution, the concentration changes to C2 and the volume changes to V2, all right? So whenever you're doing problems like the one we're about to do, you need to identify these terms in the problems, right? Usually the problem is a word problem, and you have to identify in the problem what is C1, what is V1, and so on, and what the question is asking for. So in the case of the first question, it says that 45 mils of water are added to 250 mils of a 0.75 m potassium sulfate solution. So the question is asking what will be the molarity of the diluted solution, right? So immediately I will identify this here, the 0.75 as C1, and then the 250 mils, I would identify that as V1. Now the question is, what is V2? Well, V2 would be the result when you add the 45 mils of water to the 250 mils of the solution. In other words, V2 would be equal to 45 mils plus 250 mils, which would be equal to 295 mils. All right? So therefore, to find C2, which is what the question is asking for, C2 would be equal to C1 V1 over V2. And all you have to do is put the numbers in. So C1 would be equal to 0.75 m. V1 would be equal to 250 mils. And V2 would be equal to 295 mils. So 0.75 times 250 divided by 295. So according to my calculations, the final concentration is going to be equal to 0.64 m, 0.64 m, all right? And of course, the mil units will cancel out here and here, and you'll be left with m as your final units, all right? So that's basically how you do that first example. Before I move on to the next example, let me just say that when you're using this equation, the C1 V1 is equal to C2 V2, it does not matter what the units of the concentrations are or what the units of the volume are, as long as they're the same on both sides, right? So for example, if V1 is in liters, then V2 would have to be in liters in order for you to use that equation. And that is true regardless of the units. It could be liters, it could be milliliters, it could be gallons, it doesn't matter, as long as the units are the same on both sides. And the reason why I mentioned that is because in some problems, you may be given, let's say the volume for V1 may be given in liters, and for V2, it may be given in milliliters. In that instance, what you'd have to do is either convert the liter unit or the liter value to the milliliter value, or vice versa, and then you plug the numbers into the formula and then do your subsequent calculation, all right? So that's something that you need to be aware of. Okay, any questions about the first example? Any questions? Okay, so let's look at the second example. Now in the second example, they gave you this volume of a 0.45 m potassium hydroxide solution, and it says that water is added until the final volume is 250 mils. So the question is asking what will be the molarity of the diluted solution. So again, you're going to use C2 is equal to C1 V1 over V2. And in this case, it's actually easier than the first one because all you have to do is plug the numbers that are given. So you need to identify which is which. So this would be V1, this would be C1, and the 250 mils would be V2, all right? So we just put the numbers in, 0.45 M times V1, which is 175 mils, divided by V2, which is 250 mils. And we do our number crunching. So 0.45 times 175 divided by 250. So according to my calculations, this works out to be equal to 0.32 M. Again, the mil units will cancel out, all right? So that's basically it as far as the dilution concept is concerned. And it's very important that you know how to master it because in the future, you could be working in a lab where you need to dilute a solution to a certain level. And this is basically how we do it, all right? Any questions about the second example? Any questions? Okay, so that's basically it for this chapter. This is just reviewing the topics that we covered in this chapter. So I'm going to move on now to chapter 4, which deals with aqueous solutions. Hold on, wait a minute. Let me scroll back up here. Okay, so in chapter 4, we'll be dealing with specifically chemical reactions in aqueous solutions. So we have to talk about aqueous solutions first and then move on to chemical reactions. And you're going to see that we'll be, especially at the, I would say middle to end part of this chapter, we'll be dealing with some concepts from chapter 3, namely stoichiometry, and applying it to aqueous solutions. And then at the end of the chapter, we'll be dealing with redox reactions and say more about that. So let's first talk about the electrical properties of aqueous solutions. So aqueous solutions can possess two types of electrical charge, positive and negative, all right? And in order for us to appreciate this particular concept, we need to understand the nature of charges, right? And basically, what is summarized in this diagram right here is the fact that like charges repel each other and unlike charges attract each other. So here we have some examples, and this is just purely hypothetical, of basically particles that are suspended on a string, right? So here we have two particles that are neutral. There'll be no attractive or repulsive forces, so they'll just stay put. In the case of this, where you have a positive charge in close proximity to a negative charge, there'll be an attractive force between them, so they're pulled to each other. And then in the other two situations here, where we have like charges in close proximity to each other, there will be a repulsive force here in the case of 2 plus charges, and here in the case of 2 negative charges. And if you have played with bar magnets, as I'm quite sure you have as a child, you'll see that there's some similarities between how electrical charges behave and how the different poles of a bar magnet behave, right? If you bring 2 bar magnets with the north poles close to each other or the south poles close to each other, they will repel each other. But if you put the south pole of one bar magnet close to the north pole of another bar magnet, then there'll be an attractive force between them, all right? And that's just basically the nature of these charges. Okay, so let's talk about how ions behave in an aqueous solution. So, or in a molten ionic compound. So if you have an ionic compound, and let's say it's molten, in other words, you heat it to a high temperature until you get to a liquid state, then what you'll see, if you could see the ions, you'll see the ions floating around, right? And that is different from what happens in a solid state. In a solid states, the ions are held in very rigid positions with respect to each other in an ordered way. We call this a crystal lattice structure. That's what happens in the case of molten ionic compounds. Now, in the case of aqueous solutions of ionic compounds, they also exist as very mobile in such situations. So that's what both the molten state and the aqueous state of ionic compounds have in common. they have basically the free ions that are not attracted to each other in terms of being held in a lattice structure. They're basically free floating around, all right? So basically you have the formation of anions and cations freely moving around in the solution, all right? And we can detect that this is the case because if you have this kind of setup where you have two electrodes connected to an electricity source, so this could be a series of batteries, and basically if you flip the switch, what will happen is that you'll notice or detect that an electric current will be flowing through the external circuit, which means that an electric current is flowing through the solution, all right? The reason why you have the electric current flowing through the external circuit is because you have electrons moving through the external circuit. The reason why you have an electric current flowing through the solution is because of the movement of the ions, as you can see here. So you'll notice that this electrode here is positively charged. This electrode here is negatively charged. The positively charged electrode is known as the anode. The negatively charged electrode is known as the cathode. And you'll notice in this diagram that the negatively charged ions will be attracted to the positive anode, while the positively charged ion will be attracted to the cathode. And that's the reason why the negatively charged ions are called anions, right? Because they are attracted to the anode. And the positively charged ions are known as cations because they are attracted to the cathode. So basically you have an electric current flowing right throughout the entire system, but the particles responsible for the existence of the electric current is different in the external circuit as opposed to what happens in the solution. In the external circuit, the flow of electrons is responsible for the electric current in the external circuit, while the flow of ions is responsible for the electric current within the solution, all right? So that's basically one particular property of ionic compounds, and that is that in the molten state or in the aqueous state, they will allow for an electric current to pass through it. Okay, some other things we need to say about this, or I think I may have talked about this already. Yeah, basically, this is just reiterating what I just said earlier about the anode and cathode and so on. So let me skip this here. And let's talk about now some solutions that are known as non-electrolyte solutions. And these are solutions which do not allow for an electric current to pass through it, all right? An example of this would be methanol, right? Methanol is a covalent compound. It is soluble in water, but it will not dissociate. There are no ions present in a solution of methanol. So therefore, if you try to pass an electric current through it, as is shown in this diagram here, what will happen is that nothing will happen, actually. No current will flow through. So the current, if it was flowing through, would result in this bulb or lamp lighting up. As you can see here, that's not the case. So therefore, you know that there's no electric current that is passing through the solution of methanol, and that's because there are no ions that is present in it, all right? Now, in the case of electrolytes, these can be categorized into two groups. You have one group or category known as strong electrolytes, and these are electrolytes which produces, which is a solution which contains a relatively high concentration of ions, and therefore are very good conductors of electricity, right? And a good example of this would be sodium chloride. So here we have a 1 molar solution of sodium chloride here, connected to some electrical source, maybe a battery or a generator or something like that. And here we have a lamp as a part of the circuit. And as you can see here, the lamp is lit up brightly, all right? And that's because you have a relatively large amount of ions present, which allows for the conduction of electricity within the solution. On the other hand, on the right, we have a solution here of 1 molar acetic acid. And as we're going to see later on, 1 molar acetic acid, or acetic acid itself, is a very weak electrolyte. So therefore, what that means is that it does not produce as many ions as in the case of the 1 molar sodium chloride. And therefore, as a result, it conducts electricity very weakly. And therefore, that is indicated by the lamp here, which is lit up, but not as brightly as in the case of the sodium chloride. So that's the difference between a strong electrolyte and a weak electrolyte. A strong electrolyte allows for the conductance of electricity through it very strongly, while in the case of a weak electrolyte, that's not the case. It will allow an electric current to pass through it, but not as strongly as in the case of the strong electrolyte. Okay, let's talk about the concentrations of ions in solution. We talked about concentration before. Remember we said that the concentration can be expressed in several units. The one that we were introduced to in chapter 3 was the mole per liter unit, right? The number of moles in 1 liter of the solution. Now, in chemistry, there's a symbolism that is used to represent concentration, and that is what you see here, square brackets. So basically, if you see something like this, let me squeeze it up here. If you see something like this, right? What this means is concentration of sodium chloride. All right? So that's what this symbolism means, the square brackets or the square parentheses. It means the concentration of whatever is within the square parentheses. All right? So let's think about what happens in the case of sodium chloride when it dissolves in water. Like any other ionic compound, sodium chloride will undergo complete dissociation. In other words, the sodium chloride will break up to form the sodium ions and the chloride ions as described by this equation. So therefore, based on this equation, we can come to the conclusion that whatever the amount in terms of moles of sodium chloride that you start off with, the moles of sodium ions and the moles of chloride ions will be the same. So therefore, if the solution originally was 0.010 m sodium chloride, that means that the concentration of Na plus would be 0.010, and the concentration of chloride ions will also be the same, 0.010. And I might add that the total concentration of ions, let me write this down here, or let me just write it over here. The total concentration of ions would be equal to 0.0100 m plus 0.0100 m, which is equal to 0.0200 m. All right, so you could be asked to determine the total ion concentration of a particular solution of an ionic compound, and that's basically how you do that. Now let's look at another example, this time, of a 0.010 m solution of sodium sulfate. So again, if you look at the stoichiometry of the dissociation, you'll see that for every 1 mole of sodium sulfate that goes into solution, it will produce 2 moles of sodium ions and 1 mole of sulfate ions. So therefore, in terms of the concentrations of the respective ions, the concentration of sodium would be 0.020 m, and the concentration of the sulfate ions would be 0.010 m. And again, if you're asked to find the total concentration of all the ions, then it would simply be 0.020 plus 0.010, which would be equal to 0.030 m, all right? So that is something that you need to be aware of when it comes to determining the concentration of ions of a solution of an ionic compound. You have to take into account the dissociation, the number of moles of the ions present or formed per mole of the original compound that goes into the solution. Okay, any questions about this? Any questions about ion concentrations in solution? Any questions? Okay, so let's talk about strong and weak acids. Now, earlier we talked about strong and weak electrolytes. If you understood that, then you should have no problem understanding the term strong and weak acids. It's the same underlying principle. Basically, it's based on the level or the extent of dissociation that these compounds will undergo when they're added to water. So in the case of strong acids, these are acids that undergo complete ionization when added to water. And also, they are very good conductors of electricity, all right? Now, weak acids, on the other hand, is basically the opposite. They undergo partial dissociation, which means that only a small fraction of the acid molecules will undergo dissociation. And therefore, as a result, the amount of ions present will be relatively small, and therefore, as a result, the resulting solution will not be as good a conductor as in the case of strong acids, all right? And in terms of how we represent the dissociation, in the case of strong acids, we use a one-direction arrow to indicate that all the acid molecules are undergoing complete dissociation, whereas in the case of weak acids, we use a double arrow to indicate that the dissociation is not a complete dissociation. So in the case of organic acids like acetic acids, which are weak acids, you'll see that basically the dissociation is represented like this, all right? You have the acid molecule over here, you have the ions being formed here, but you'll notice that you have arrows pointing in both directions. And basically what this means is that you have a back and forth taking place, right? You have the forward reaction taking place, and at the same time, you have the reverse reaction taking place. And when the rate of the forward reaction is equal to the rate of the reverse reaction, we have what is known as a state of dynamic equilibrium, all right? And for those of you who have to do general chemistry 2, you're going to learn a lot about equilibrium systems. In fact, depending on the textbook that you'll be using, this principle of dynamic equilibrium will probably be found in 2 or 3 chapters, right? It's a very extensive topic that is very important in terms of understanding equilibrium systems, all right? So that's what happens in the case of weak acids. Now, in the case of strong acids, let me just squeeze that up here. Like hydrochloric acid, all right? When that undergoes dissociation, the dissociation will be complete. So therefore, this is what's going to happen. All right? So this is a strong dissociation because hydrochloric acid is a strong acid. And you'll notice that the type of arrow that is used, okay, what's going on here? The type of arrow that is used is a one-directional arrow as opposed to the 2 arrows going in opposite directions in the case of weak acids, right? So that's how we represent the dissociation in the case of strong acids. The arrow going from one direction from the undissociated molecules to the ions. In the case of weak acids, the arrow that is used, well, 2 arrows are used going in opposite directions, all right? Okay, so how do we recognize strong acids and weak acids? Well, typically, the convention normally used is that when you're writing down the formulas for strong acids, you place the hydrogen first, all right, in the formula. So for example, HCl, H2SO4, those are strong acids. Weak acids tend to have the hydrogens placed at the end. Now, this is not always observed, but this is a normal convention that is usually observed. So what I would suggest you do is that you memorize these 6 acids as strong acids, all right? Hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric acid, and perchloric acid. Pretty much all other acids that you will encounter will be weak acids. And if there are any other acids that are strong acids, I will certainly make you know about that. But pretty much all other acids that are not on this list are basically weak acids. Now, let me just say something here about sulfuric acid in this list, because as you can see, in the case of sulfuric acid, there are 2 hydrogens here, right? Now, let me go here and show you something about sulfuric acid, because sulfuric acid is a bit special in this list. So in the case of sulfuric acid, H2SO4, it turns out that the first dissociation to release a proton or hydrogen ion is very strong, all right? Whoops, HSO4 minus aqueous, all right? So the first dissociation to produce 1 hydrogen ion is strong. However, the second dissociation, so this here, we're going to write down here, start off with here. And then when that loses a hydrogen ion, you're going to end up with SO4 2 minus aqueous. And it turns out that this is a weak dissociation. So in actual fact, you should have 2 arrows pointing in the opposite direction. So 1 arrow point this way, the other arrow point that way, all right? So sulfuric acid is a bit different from the other strong acids that I showed you on that list because it has 2 hydrogen ions that can be released. The first one is going to be released strongly, but the second one will be a weak dissociation, all right? So I thought I should just mention that so that you're aware of that. Okay, so those are the 6 strong acids that you need to know. Pretty much all other acids that you'll encounter will be weak acids. Okay, so let's talk about bases, strong and weak. And again, it's the same concept that applies. Basically, a strong base are fundamentally ionic hydroxides that will undergo complete dissociation in water. And again, because of that, they are good conductors of electricity. Weak bases, on the other hand, do not produce as many or as much by the way of ions, and therefore, as a result, does not conduct electricity as well. And again, we use a double arrow symbolism to indicate, in the case of weak bases, that the dissociation is weak. A good example of a weak base is ammonia, right? Now, you might be wondering, okay, how come ammonia is a base in any way if the formula does not contain the hydroxide ion? And the answer is that in the case of weak bases, let me go back to this again, or in the case of ammonia, when ammonia is added to water, NH3, which is a gas, is added to water, this is what happens. It forms NH4 plus, aqueous, plus OH minus, aqueous. So because the hydroxide ion is being produced when ammonia is added to water, this is liquid, then basically, because this is produced, that makes the solution basic, all right? And therefore ammonia is considered to be a weak base. Weak because you have the two directional arrow shown here. An example of a strong base would be sodium hydroxide, because sodium hydroxide, when added to water, sodium hydroxide solid, when added to water, forms sodium plus aqueous plus hydroxide ion aqueous. All right? So this is strong. I'm sorry, this is weak. The ammonia is weak. And the sodium hydroxide is a strong base. All right? Okay. What next? So that's ammonia, weak base. Okay. So as far as strong bases you need to memorize, this is actually an easier group to memorize because basically the strong bases that you'll be familiar with in this course would be hydroxides of group 1A and group 2A metals. So these are the strong bases that you need to know. Pretty much all other bases that you'll encounter will be weak bases. All right? Okay, let's see what's next. So let's talk about a neutralization reaction, which I think we talked about before. Neutralization reaction is the reaction, of course, between an acid and a base to form a salt and water. And we did some examples of that from our previous, I think it was chapter 3. Now, I think I also mentioned that the neutralization term is a bit of a misnomer because not all salts are neutral. The whole idea behind neutralization is that the acidic properties of the acid will cancel out the basic properties of the base to form neutral products. That is not always true, as you're going to learn, for those of you, again, who have to do Chem 2, you're going to learn that there are some salts that are acidic and other salts that are basic, all right? In the case of the potassium chloride example here, this is actually a neutral salt, all right? So I just thought I should mention that to you. Now, in the lab, we typically use indicators when we're doing a reaction of this type, especially analytic type exercises. And the indicator basically is used to determine the point at which you add just enough of one reactant to the other, all right? So let's say you have a certain amount of potassium hydroxide and you continue to add hydrochloric acid. You want to make sure that you add the exact amount of hydrochloric acid that will neutralize the potassium hydroxide. And we use indicators to do this. And for those of you enrolled in my lab class, you'll be doing 2 experiments known as titration, where basically this is what you'll be doing. You'll be adding an acid, you'll be adding a base to an acid, and basically you'll be, well, before you do that, you'll add the indicator to the acid, and then as you add your base, what will happen is that the color of the indicator will change well, not immediately, but at a particular point. And when that happens, you need to stop adding your base, and therefore you're going to do some measurements and so on and determine the concentration of one based on the other. So that is something for you guys to look forward to. Now, let's talk about writing down what is called the Net Ionic Equation for a reaction of the type that we just described. When you're writing down or determining the Net Ionic Equation, what you're actually determining is the actual reaction that is taking place. Because what you're going to see in this example is that not all the species that are involved in a reaction is actually actively a part of the reaction. You're going to have some species that will be actively reacting, and then you're going to have other species which will just basically not be participating, and we call these the spectator ions, all right? So the example we're going to use here is the example of the potassium hydroxide reacting with hydrochloric acid to form water and potassium chloride. Now, remember we said that hydrochloric acid is a strong acid. We also said that potassium hydroxide is a strong base, right? And also potassium chloride in an aqueous solution, because it's an ionic compound in an aqueous solution, that will also be a strong electrolyte and will undergo complete dissociation. So therefore, we're going to have three species that will undergo complete dissociation: the hydrochloric acid, the potassium hydroxide, and the potassium chloride. The water is a molecular compound and it will not undergo dissociation. So what we're going to do in the next line is write down all the species that will exist after dissociation. And that's what we have here. The HCl here will be dissociating to form H plus and Cl minus. The KOH will dissociate to form K plus and OH minus. The water will remain intact, so we leave that as it is. And the potassium chloride, because it's an ionic compound in an aqueous solution, that too will undergo complete dissociation to form K plus and Cl minus, all right? Now, some terminology here that I need to introduce. This first equation here is called the molecular equation. Let me write it down here. Molecular equation. All right. So, and let me just say that this term molecular equation is a bit of a misnomer because not all the substances obviously are molecules, but that's basically the term that is used for that equation. Now, the next equation that results from the dissociation of the different, the strong acid, strong base, and the potassium chloride, this is called the ionic equation. So let me write this down here, ionic equation, all right? Okay, now, if you look at the ionic equation carefully, you'll see that there's certain items or ions that are common to both sides, all right? Namely, you have a chloride ion here and a chloride ion here. You also have a potassium ion here and a potassium ion here. So basically these ions remain unchanged as you go from reactants to products. In other words, these ions are the spectator ions, all right? And therefore what we can do to the spectator ions is cancel them out. So therefore the chlorides will be canceled out as well as the K plus will be canceled out. And therefore all we have to do from here is write down what is left. And basically that's it. H plus OH minus plus the OH plus the H2O, I'm sorry, all right? And this equation is a net ionic equation because this is basically showing you what is actually happening as far as the reaction is concerned. Basically what's happening is that the H plus is combining with the OH minus to form the water molecule, all right? So that's basically how you determine the net ionic equation. One more thing I should mention here, which I probably should have mentioned before. Whenever you're trying to determine what the net ionic equation is, you need to start off with a balanced molecular equation to begin with, all right? So you have to ensure that the first equation is balanced, and then you go through the steps, all right? In fact, let me do another example. Let me remove this here. Okay, so let's say you're given H2SO4 plus CuOH2. All right, now, of course, you should be able to figure out what the products would be, which would be CuSO4 plus H2O. All right, so to balance this, we need a 2 here. And also we need to include the state symbols, AQ. Hold on 1 minute. Copper 2 hydroxide, I think, is a solid. Okay, so let me do solid here. This will be aqueous for sure. I know that much. And this will be liquid, all right? Okay, so this would be the molecular equation. Molecular equation, all right? So the next step is the ionic equation. Now, in the case of sulfuric acid, remember I said that only one of the two hydrogens will undergo, will be ionized strongly. So therefore this will produce, what am I doing? Let me erase this here. So this will produce H plus aqueous plus HSO4 minus aqueous. All right? And then for the copper 2 hydroxide, because it's in a solid state, there'll be no dissociation. So we're just going to leave this as it is. Solid. And then on the product side, we have copper 2 sulfate, which is aqueous. So that will dissociate to form Cu2 plus aqueous plus SO42 minus aqueous. And the water, again, as we saw in the previous example, will remain intact because it's a molecular compound. So this would be the ionic equation. Okay, so the question is, will anything cancel out in this case? And looking at this, the answer will be no. There's nothing that will cancel out because we don't have anything common to both sides. So not only would this be the ionic equation, this would also be the net ionic equation. And that's basically all that you can do with this, all right? So that's just another example of how you can determine the net ionic equation for a reaction, all right? For a reaction, a neutralization reaction, I should say. Okay, any questions about this? Any questions? Any questions? Okay, so I mentioned titration before. This is just basically rehashing what I just said with a little bit more detail. So let me just go into this briefly. So basically one reactant is placed in a long cylindrical piece of glassware known as a burette. As I said before, those of you who are doing the lab with me, you'll get the opportunity to work with that piece of glassware and you'll see how the setup takes place. The burette basically measures the amount of liquid that is dispensed from it. And in the experiment that you'll be doing, at least one of them, you'll be using the burette to dispense the base, all right? And the other reactant will be placed in a flask along with a few drops of the indicator. So the other reactant in the experiment that you guys will be doing will be the acid, which will be placed in a flask, and then a few drops of the indicator will be added. And you're going to run the solution from the burette into the flask until you get the color change. Once the color change occurs, you immediately shut off the burette and then you record the volume of the base that is added to the acid. And then you'll do some calculations to determine, you know, the concentration of one or the other. If I remember correctly, in the experiment that you'll be doing later on this semester, you'll be determining the concentration of the base and then use that to do something else. I don't remember exactly right now, but you know, that's something that you'll be doing later on. Okay, there's some other acid-base reactions which involves the formation of gases, all right? And these are shown right here. Now, this is based on certain anions being present in a particular ionic compound, these anions right here. So in the case of any compound that contains the bicarbonate or the carbonate ions, if you add anything acidic to it, you're going to get carbon dioxide gas along with water. And this is actually something you can do at home safely. Because, for example, the bicarbonate ion is present in baking soda, all right? And if you squeeze some lemon juice, as you can see here, you're going to see some bubbles, right? Lemon juice contains an acid known as citric acid, right? So basically what will happen is that the hydrogen ions from the acid will react with the bicarbonate ions from the base, or from the baking soda in this case, to form carbon dioxide. You can also use, instead of lemon juice, you can use vinegar, because vinegar contains acetic acid, which does basically the same thing, all right? In the case of compounds containing hydrogen sulfide hydrogen sulfite or sulfite ions, if you add acid to this, any compounds that contain any one of these two, you're going to end up with the formation of sulfur dioxide gas. Now, the thing about sulfur dioxide gas is that it is very, what's the word I'm looking for? If you're in a room filled with sulfur dioxide gas, you'll be coughing and choking and all of that. So obviously, I certainly would not recommend doing this at home, all right? But of course, it's something that you need to know. And then finally, any compound that contains the hydrogen sulfide or sulfide ions, if you add acid to them, they'll form hydrogen sulfide gas, all right? Now, this particular type of reaction, I definitely would not recommend that you do at home for two reasons. One, the hydrogen sulfide gas is very awful smelling, smells like rotten eggs, all right? And two, more importantly, hydrogen sulfide is very toxic, very poisonous. So if you inhale enough of it, then you can literally die, all right? So I would not recommend that you do this at home. But again, this is something that you need to be aware of. Okay, now let's talk about precipitation reactions. I'm looking at the time here. All right, let me just start talking about it and then we'll continue after the break. So when we're talking about precipitation reactions, we are talking about reactions where you have two clear solutions, right, containing ions. And then when you mix them, you have the spontaneous formation of a solid, right? And that solid is called a precipitate, okay? So an example is shown here. Now, if I'm not mistaken, what we're observing here is a reaction between lead ions. I think if I'm not mistaken, it's, let me write this down. PbNO3 to aqueous plus potassium iodide aqueous solution. And what you'll find is that the lead will come together with the iodide to form lead iodide, which is a solid. So the solid that you see here, I think, is lead iodide. And the other product would be potassium nitrate, which would be in an aqueous solution, all right? So the formation of this solid here from these two aqueous solutions is what we call the precipitate, all right? So there's a lot of examples of precipitation reactions we can talk about. Now, before we do that, however, we need to understand how do we determine whether or not a product is going to be a precipitate. Well, this is based on the solubility of the product, right? If the product is insoluble in water, then it will not dissolve in water and therefore would come out as a precipitate. And there are some rules that would be useful for you to determine whether or not a particular ionic compound would form a precipitate, right? We call these the solubility rules. Now, you don't need to memorize them. In fact, these rules are posted in Canvas in that tables, you know, the list of tables, one of them, one page, you'll see this particular chart, right? However, it's very important that you know how to use this particular chart. So for example, if you look at the first line here, it says that almost all nitrates, acetates, perchlorates, group 1A metal salts, and ammonium salts are soluble, right? So pretty much any compound that fits this criteria here, or these criteria, will be soluble in water. And then the next line says, most chlorides, bromides, and iodides are soluble, but there are some exceptions, namely lead 2+, silver+, and mercury 1, all right? So any compound that fits this second line here would be soluble with the exceptions of the lead 2+, silver, and mercury 1, and so on and so forth. So, you know, this is basically a table that you're going to refer to in order for you to make certain predictions as to whether or not a precipitate will form, all right? Okay, and these are just some examples of precipitation reactions and their applications. So I'll just point to, for example, this one right here. If you mix a solution containing silver ions with bromide ions, you're going to get this solid being formed. And this is, the application would be where the silver bromide is prepared for use in photography, basically, all right? And these are just some other examples as well. Okay, what I'm going to do is take a break here, and then we're going to look at some examples of precipitation reactions. And after that, we'll talk about redox reactions, all right? So 10-minute break, and then we'll be back at 10 o'clock, all right? Okay, so let's proceed from where we left off. So we were talking about precipitation reactions. Let me share my screen again. Okay, so I take it you can see my screen now, right?
Yes.
Okay, so what you see here is the reaction I was alluding to earlier. The reaction between, oh shoot, what did I do wrong? Oh shoot, let me see here. I keep touching this button that I'm not supposed to touch. Okay, what, I hate when things like this happen. Oh my goodness, all right. I don't know what I did wrong. All right, you know what? Let me get over this and restart. Aqueous plus 2 potassium iodide aqueous to give PbI2 solid plus 2K NO3. Okay, so you're given this equation, right? Now, I've done this already for you, but you know, sometimes you might be asked, or you may have to determine which of these would be a solid and which would be aqueous. And the answer to that, of course, is going back to the chart I mentioned earlier. Let me show you again. Oops. That chart, all right? So if you look at this chart, you see that it says that most iodides are soluble with the exception of lead 2+, right? And in the example that we have here, lead 2 iodide would be solid, right? According to the rules, all nitrates are aqueous, so we know that, or all nitrates are soluble, so therefore we know that this would be aqueous, and we know that this would be aqueous, and we know that all group 1A salts are soluble, so we know that potassium iodide would be in an aqueous solution as well, all right? So, you know, that's how we use the chart to help us to determine what is soluble and what would be in the aqueous state and which would be in the solid state. Now, what we're going to do is go through some steps which are similar to what we did for the neutralization reaction to determine the net ionic equation for this reaction. So these principles will apply as we looked at in the previous examples that we did earlier. So this would again be the molecular equation. All right. And then we have to determine which of these will dissociate. Now, any ionic compound in an aqueous solution will undergo complete dissociation. So that means that this will dissociate, and the potassium nitrate over here will dissociate because they're all ionic and they're all in an aqueous state, all right? So therefore, in the case of lead, so to get the ionic equation, that's what we're doing here, the lead 2 nitrate will dissociate to form Pb2+ aqueous plus 2NO3- aqueous. And of course, we have a 2 here because we have 2 here for the nitrate, all right? Plus 2K+ aqueous plus 2I- aqueous, all right? Again, we have a 2 here, so that 2 multiplies the potassium and the iodide. So that's why we have the 2 here and we have the 2 here. And then on the product side, we have this ionic compound, which is in a solid state. So that will not dissociate, that will remain intact. PbI2, solid. And then in the case of the 2 potassium nitrates, that will dissociate to form 2K plus aqueous plus 2 NO3 minus aqueous. All right? So that would be the ionic equation. So to get the net ionic equation, we look for the spectator ions. And in the case of this particular example, the nitrates would be the spectator ions, so we can cancel them out. And the potassiums will be the spectator ions, so we can cancel those as well. And we'll be left with Pb2 plus aqueous plus 2I minus aqueous. Same thing happening again. Hold on, let me see here. To give PbI2 solid, and that would be the net ionic equation. All right. So as you can see, it's very similar to what we did in the case of the neutralization reactions. There are some differences, but basically what you should look for are those substances that will strongly dissociate, and you write down the products of their dissociation. The substances that will not dissociate are any ionic compound in the solid state or any molecular compound. All right, those will not dissociate. But pretty much any ionic compounds in the aqueous state will undergo complete dissociation. All right. Once you determine which ions will dissociate, the next thing you need to look for is the spectator ions. Once you cancel those spectator ions out, then what is left would be the net ionic equation. All right. Okay. Any questions about this example? Any questions? Any questions? Okay, so let's see if we can do another example. So let me get rid of this here. And okay. Okay, sorry about that. Okay, so the next example we're going to look at is Na2SO4 aqueous plus BaCl2 aqueous. Okay. Now, my question to you at this stage is, what would you expect the products of this reaction to be? Anybody?
Sodium chloride and barium sulfate.
Okay, so the formula for sodium chloride is?
NaCl.
Oops. NaCl. And the formula for barium sulfate is?
Ba2SO4.
Not quite. What's the charge on the barium ion? You can refer to the tables I've posted in Canvas.
Oh, BaSO4.
Okay, it's BaSO4, exactly. Because the barium has a +2 charge and the sulfate has a -2 charge, all right? Okay, so the next step is to balance this equation. So how would we balance this equation?
Put a 2 on the sodium chloride.
Okay, very good. All right, and that's all we need, right? Okay, now here's the next step. We need to find out which, if any, of these products would form a precipitate. So in order for us to do that, we have to go to the solubility rules. So let's deal with the sodium chloride first. And let me go to the solubility rules here. So based on the solubility rules here, would you expect sodium chloride to form a precipitate?
Yes.
Why?
Because it's a chloride.
Well, let's see what this says about chloride. It says most chlorides, bromides, and iodides are
Soluble.
soluble. There are certain exceptions, but sodium is not one of them, right? So therefore, sodium chloride will be soluble in water, right? And because it's soluble, we're going to put AQ here. All right? So that's as far as the sodium chloride is concerned. What about the barium sulfate? Well, let's go to the chart again. What does it say about sulfates?
Most are soluble.
Okay, but what about the exceptions?
Yeah, barium is.
Barium is an
not.
exception, right?
Yeah.
So therefore, what that means is that barium sulfate would not be soluble in water, and therefore, it would precipitate, would form a solid. All right? Okay, so that's very important. We need to know which products would form a precipitate, if any, all right? Now, the next step is to get to the ionic equation. And if you remember, we said that any ionic compound which is in an aqueous solution will dissociate to form the ions, right? So in the case of sodium sulfate, this will dissociate to form 2Na plus aqueous plus SO42 minus aqueous. And then the barium chloride, which is also in an aqueous solution, would form Ba2 plus aqueous plus 2Cl minus aqueous. And then on the product side, we have the sodium chloride, which is also in an aqueous state. So that would be 2Na plus aqueous plus 2Cl minus aqueous. And then finally, we have the barium sulfate. It's in a solid state. So that means that that does not dissociate. So you're going to end up with Ba2 plus, I'm sorry, BaSO4. What am I saying? Solid, all right? So that would be the molecular equation. I'm sorry, that would be the ionic equation. The first equation is the molecular equation. Now we have the ionic equation. So what do we do next? We cancel out the spectator ions. So can anyone tell me what the spectator ions are in this case? Which ions are the same on both sides?
The aqueous sodium.
Exactly.
Aqueous.
Right, sodium aqueous and
The chloride too.
exactly. And all we have to do is write down what is left, which would be, excuse me, SO42 minus aqueous plus Ba2 plus aqueous to form BaSO4 solid. And that would be the net ionic equation. All right? So, you know, based on what we have just done, you should be able to determine the net ionic equation for any reaction that you're given. Okay, any questions about this particular example? Any questions? Any questions? Okay, so let's move along now to a discussion of redox reactions, right? So we have to talk about the terms oxidation and reduction. And this is based on the fact that there are some chemical reactions that involve changes in what is known as the oxidation states of atoms. And the oxidation states are represented by what are known as oxidation numbers, which would be essentially equal to the charge on a monatomic ion. So as an example, when sodium, the atom, loses an electron, it forms the sodium ion, and therefore the oxidation state of the sodium ion will be the charge, which is +1. Now, what we're going to see here is how do we determine the oxidation number or the oxidation state of different atoms in a molecule or an ionic compound. So just to give you the definition of oxidation number, it's a charge the atom would have in a molecule or an ionic compound if the electrons were completely transferred. And it's basically used as a measure of the level of oxidation of a particular atom in a compound or an ion, or by itself even, all right? So these are the rules that you need to know in order to determine the oxidation number of particular atoms. The first is pretty simple. Free elements, in other words, elements that are not combined with anything else, will have an oxidation number of 0. So it doesn't matter what the element is. It could be sodium, beryllium, potassium, lead, hydrogen, oxygen, or phosphorus. If it's by itself, if it's not combined with anything else, then the oxidation number of that element is 0. Now, in the case of monatomic ions, the oxidation number will be equal to the charge that is present on the ion. So for example, in the case of the lithium ion, the oxidation number or the oxidation state is +1. In the case of iron, 3+, the oxidation number is +3. And in the case of the oxide ion, the oxidation number is -2, all right? So that's basically how you determine the oxidation number of an element in a monatomic ion. Now, in the case of oxygen, if it's combined with another substance, then its oxidation number is usually -2, but there's an exception, and the exception would be in the case of peroxides. The oxygen in peroxides would have an oxidation number of -1, all right? So basically, for pretty much all other compounds where oxygen is combined with something else, the oxidation number of oxygen is -2, but if the oxygen is a part of the peroxide structure, then the oxidation number of the oxygen in those compounds would be -1, all right? Okay, some other rules, and this rule has to do with hydrogen. The oxidation number of hydrogen is usually +1. The only exception is if the hydrogen is combined directly with a metal, in which case the oxidation number would be -1, all right? So an example of, let me see here. Where is that? Okay. So an example in the case of, in the case of, let's say, HCl, the oxidation number of hydrogen is +1, but in the case of sodium hydride, the oxidation of hydrogen is -1, right? Because in this case, the hydrogen is combined with a metal, all right? Okay. Rule number 5, group 1A metals are always +1, group 2A metals are always +2, and fluorine is always -1 in compounds that contain these elements, all right? So, it doesn't matter what they're combined with. So in the case of, let's say, sodium chloride, the oxidation number of sodium is +1. In the case of magnesium chloride, the oxidation number of magnesium is +2. And in the case of calcium fluoride, the oxidation number of fluorine is -1, all right? So that's basically rule number 5, which deals with group 1A, group 2A metals, and fluorine, all right? Now, number 6, rule number 6 is very useful for determining the oxidation number of other elements that were not mentioned before. And this rule says the sum of the oxidation numbers of all atoms in a molecule or ion is equal to the charge on the molecule or ion, all right? So for example, let's look at this ion here, the bicarbonate ion. Question is asking, what's the oxidation numbers of all the atoms in this particular ion? Well, we know based on previous rules that the oxidation number of oxygen is -2, and for hydrogen it's +1, right? So we know those two directly based on the previous rule. What we don't know directly is the oxidation number of carbon, but we know that the sum of the oxidation numbers of everything will be equal to the charge based on rule number 6. So we can set it up like this. 3 times the oxidation number of oxygen, which is -2, because we have a 3 here, +1, which is the oxidation number of hydrogen, plus the unknown for carbon. The sum of all of those will be equal to -1. So all we have to do is solve for the question sign. And when you do that, you see that the oxidation number of carbon works out to be equal to +4. All right, so indirectly, we can determine the oxidation number of carbon based on our direct knowledge of the oxidation number of hydrogen and oxygen, and also based on the fact that the sum of the oxidation numbers would be equal to the charge on the particular ion as per rule number 6. Okay, so those are the rules when it comes to determining the oxidation numbers of different atoms. And in fact, let me just do one or two more examples so that you get a good feel for how we solve these kinds of problems. So let's say you're given K2CR2O7, all right? And let's say you're asked to determine the oxidation number of the chromium in this compound, all right? Well, based on the rules that we just talked about, we know that the oxidation number of potassium is +1, and we know that the oxidation number of oxygen is -2, all right? So what we need to find is the oxidation number of chromium, which I'm gonna call X, all right? So the way we would set this up is that because there are 2 potassiums here, I'll multiply the +1 by 2, and then I would add to that X, 2X, which we don't know, 2 because we have 2 chromiums here, plus 7 times -2 for the oxygen, because we have a 7 here, all right? And the sum of all of that would be equal to the total charge on the entire compound, which is 0, all right? So all we have to do now is solve for X. So just a bit of algebra here. So this simplifies to 2 plus 2X minus 14 equals 0. Which simplifies to 2X minus 12 equals 0. Which simplifies to 2X equals to 12, which means that X is equal to 6. So therefore, the oxidation number of chromium in this compound would be +6. And that's basically how you do that. All right? Any questions about this one? Any questions? Any questions? Okay. Whoops. Wrong PowerPoint. Let me see here. Okay. So now we're going to look at how do we identify redox reactions, right? A reduction oxidation reaction is one where the oxidation number of an atom changes during the reaction, all right? And the change in oxidation number can either increase or decrease. Now, if the atom's oxidation number increases, then we say that that particular atom is being oxidized, right? Or oxidation is taking place. And what you're going to see is that this corresponds to a loss of electrons. On the other hand, if the oxidation number decreases, then we say that reduction takes place. In other words, there's a gain of electrons occurring while this is taking place, while the oxidation number decreases, right? So we simply call it a redox reaction. And what you'll find is that you cannot have one without the other, right? If oxidation takes place, then reduction must have taken place elsewhere, all right? Because when an atom loses electrons, then those electrons will be transferred to another atom, which will undergoing the reduction. Okay, so just to point out a simple example of a redox reaction, and then we'll move to more complicated examples. We're going to look at this setup right here. Now, what you're looking at here is a simple reaction where magnesium in the form of a coil is placed in a solution of copper 2 sulfate, all right? Copper 2 sulfate has a blue solution due to the copper 2+ ions that are present in that solution, all right? And what will happen is that if you wait a while, you'll see that the blue color will start to clear up. So it becomes looking like this over here on the right. And in addition, you're going to see some deposits left on whatever is remaining of the magnesium that is present in this setup, all right? So 2 things you'll be observing. The blue color will clear up and a deposit will be formed on the magnesium that is left behind, all right? So how do we explain this? Well, what is happening is the following reaction. Let me write it up here. The reaction that is occurring is Cu2+ aqueous. In fact, let me correct that. Well, not correct it, but let me write it in a different way. Let me get my eraser and erase this here. And then let me get back to my pen. Okay, so the copper sulfate aqueous will react with the magnesium solid to form magnesium sulfate aqueous plus the copper solid, all right? So the copper solid is what is deposited. You see these, these deposits right here. That's the copper being deposited, all right? Okay, so this is a reaction that is taking place. Now, if you were to write down the net ionic equation, just like we did in the previous examples, I won't go through all the steps, you'll be left with this. Whoops, I need to plug this in. Ugh. Okay, so if you were to write down the net ionic equation, you'll be left with Cu2 plus aqueous plus Mg solid to form Mg2 plus aqueous plus Cu solid, all right? So this would be the net ionic equation for this reaction. And you're going to notice that there's some changes in the oxidation number of both reactants on the left side. For one, the copper 2 plus will undergo a change in oxidation number from +2 here to 0 over here. And that's because the copper 2 plus is gaining 2 electrons, all right? In other words, according to the definition that we saw earlier, the copper 2 plus is undergoing reduction, all right? So that's what's happening to the copper 2 plus. It's undergoing reduction to form the copper metal. On the other hand, the magnesium is undergoing a change in the oxidation number from 0 on the left to +2 on the right. So in other words, the magnesium is losing 2 electrons. I hope you can see what I'm writing here. In other words, the magnesium is undergoing oxidation. All right? And that is what happens in every redox reaction. You have one species that is losing electrons and another species that is gaining electrons, right? And as I said before, it is impossible to have oxidation without reduction, or vice versa. Another thing I want to say here, and this will become important in some problem-solving exercises that we're going to see shortly. You'll notice that the total number of electrons that is lost by the magnesium here is equal to the total number of electrons that is gained, that is gained by the copper 2 plus. And that is true for every redox reaction. The number of electrons lost must be equal to the number of electrons gained. In fact, aqueous plus 2 electrons to give you Cu solid, and Mg solid to form Mg2 plus aqueous plus 2 electrons, all right? That's another way of representing what we were discussing here. So this is the reduction half reaction, we call it, and this is the oxidation half reaction, right? And as you can see here, the number of electrons lost and gained would be the same. So when you add these two together, the electrons will cancel out and you'll end up with the net ionic equation, which is Cu2 plus aqueous plus Mg solid to give you Cu solid plus Mg2 plus aqueous, all right? So this is another way of showing you how the redox reaction takes place in the reaction between the copper 2 plus ion and the magnesium solid. Okay, any questions about this example? Any questions? Any questions? Okay, so how do we balance redox equation? Because admittedly, the one I just showed you, that's a very simple example. There are much more complicated ones which we're going to talk about. And because of the level of complexity of these reactions, we cannot balance these redox reactions in the same way that we would balance any ordinary reaction. I mean, you can, but it will be a very long and tedious process. So the method I'm going to describe here is a better method. It's a bit long, but if you follow the steps as outlined here, then you should be able to balance any redox reaction without any hiccups whatsoever. So basically, the best way to do this, to show you how to do this, is to go directly into an example. So here's a reaction between Fe2 plus and Fe3 plus to form, well, I'm sorry, between Fe2 plus and dichromate ion to form Fe3 plus and another product. So this is the unbalanced equation here, all right? So the first step that you need to follow is that you separate this unbalanced equation into two half equations, all right? One half equation would represent oxidation, and the other half equation would represent reduction. So the oxidation half equation in this case would simply be the Fe2 plus to form the Fe3 plus, all right? And then the reduction half equation would be the dichromate, which is Cr2O72 minus, forming the Cr3 plus, all right? So that's what you need to do first after you know what the unbalanced equation is. You separate it into two half equations, all right? The next step is that you balance all atoms excepting oxygen and hydrogen in each half equation according to the way that we're familiar with. So in the case of the oxidation, we don't need to make any changes here because we have one iron atom here, one iron over there, so that's balanced. On the other hand, in the case of the dichromate going to the Cr3 plus, you have two chromiums represented here, you have one chromium here, so we need to place a coefficient of 2 in front of the chromium 3 plus. So that's why we have this 2 right here, all right? So that's very important. You make sure that you balance all other atoms excepting oxygen and hydrogen, all right? Now, after you have done that, what we'll be looking at basically is for reactions under acid conditions, right? So what we need to do next is to balance the oxygen atoms, firstly, and then balance the hydrogen atoms. So let's balance the oxygen atoms firstly. Now you'll notice that you have 7 oxygens here. So to balance the oxygen atoms, what we do is add enough water molecules to the other side so as to achieve that balance. So since we have 7 oxygens here, we have to add 7 water molecules here. So now we have 7 oxygens here, 7 oxygens here, so that's fine, all right? Then we balance the hydrogen atoms by adding H plus ions. So you'll notice, let me back up a bit. You notice that there are 14 hydrogens here. So what we need to do is add 14 hydrogen ions on this side, like that. And now we end up with the hydrogens balanced and the oxygens balanced, all right? Okay, the next step is that we add electrons to each half reaction so as to balance the charges. And let me just warn you that this is where students, this is a step in this process where students tend to make errors, all right? So I'm going to go through this slowly so that you understand how this is done. Now remember, when you add an electron to a side, basically you're reducing the total charge on that side by 1 because each electron carries a negative charge. So in the case of this half reaction here, we have Fe2 plus on this side, Fe3 plus, right? So basically, to make sure that the total charges on this side is the same as on this side, what we do is add 1 electron, because by adding 1 electron, let me just write something here. Remember now, this is plus 3. If we add 1 electron here, what we're doing is minusing 1 charge from that total, and that will give you plus 2, which balances with the plus 2 on this side, all right? So that's the reason why we add 1 electron to the right side of the first half equation. Now for the second half equation, okay, you know what, let me erase to avoid confusion. Let me erase what I just wrote. Okay, for the second half equation, you'll notice that before you add these electrons, so, okay, what's going on here? Okay, so before we add these electrons, right? You'll notice that you have a total of plus 14 minus 2 for these 2 negative charges here. And over here, we have a total of plus 6, right? So this gives you a total of plus 12. And we have plus 6 on this side. So in order to get the charges equal on both sides, what we do is add 6 electrons, because by adding 6 electrons, you're adding 6 negative charges to the plus 12, and that will give you a total of plus 6. So the 6 plus charges will balance with the 6 plus charges here, all right? So that's basically what you do in order to balance the charges in either case. You add electrons such that, and you have to add electrons to one side, such that the number of charges total, the net charges total, will be the same. And basically what you need to do is add electrons to the side with the higher net charge. Because going back to this example here, okay, okay, we had plus 12 here, and we have plus 6 here. So because this is higher, we add electrons to this side, and in this case, we would add 6 electrons to get this side reduced to plus 6, which balances with the plus 6 on that side, all right? Okay, so we're not finished yet, believe it or not, because the next step involves something that we talked about earlier. If you recall, I said that in any redox reaction, the number of electrons lost and gained must be the same. Now, if you look at these two half equations, you'll see that, okay, what's going on here? You'll see that the number of electrons lost here is 1, and the number of electrons gained here is 6. So obviously, we need to do something in order to ensure that the number of electrons lost and gained are the same. And basically what we need to do is to multiply either one or both half equations by the appropriate integers in order to achieve equality in the number of electrons lost and gained. So what we do in this case, obviously, is that we would multiply the first equation by 6, and we leave the other equation alone because it already has 6 electrons, as you can see here. And basically what we will do next is add these two equations together. Now that we have, show you here, now that we have 6 electrons here and 6 electrons here, all right? Now that we have that situation, all we have to do is add the two half equations. And of course, when you're adding these two half equations, the electrons must cancel out, as you can see here and here. And there's nothing else to cancel out. We're going to look at some examples where other items will cancel out, but for now, nothing else will cancel out in this case. And all we have to do is write down what is left, and that would be the final answer, or I should say that should be the final answer, all right? Now, I normally suggest to my students, in fact, I would strongly recommend that when you get your final answer or what you think is the final answer, you do a final check through to make sure that everything is balanced, right? So as stated here, you verify that the number of atoms and the charges are balanced. And in terms of the atoms, let's go through the whole equation to see if that's the case. You have 14 hydrogens here. You have 7 times 2, 14 hydrogens, so that's balanced. You have 2 chromiums here. That's balanced. You have 6 irons here, 6 irons here, that's balanced. And in terms of the charges, when you add up all the net charges on this side here, which is 14 minus 2 minus 6 times plus 2, 12, you're going to get 24. And the same thing will be the result on this side. 6 times 3, 18. 18 plus 2 times 3, 6. That gives you 24. So therefore, the charges are balanced. And therefore, you can be confident that this is indeed the correct answer. All right? Okay, any questions about this particular example? Any questions? Any questions? Okay, we're going to do a couple of more examples because I think it's important that, you know, you understand what to do at each stage. So what I'm going to do is switch to my writing pad here, and I'm going to clear this. And I'm going to start off with this first example of MnO4 minus plus C2O4 2 minus to give Mn2 plus CO2. Okay, so let's say you're given this to balance, all right? Now, if you recall what we did in the first example, the very first step is that we separate this equation into two half equations. So one half equation is going to be MnO4 minus to form Mn2 plus, and then C2O4 2 minus to form CO2, all right? So that's the first step. Now the second step is that we balance all atoms excepting oxygen and hydrogen. So in the case of the first half equation, that would be manganese, but we don't need to do anything because there's one manganese here and one manganese here, so that's fine. However, in the second half equation, we have two carbon atoms here and we have only one here. So what we do, we put a 2 there, all right? So that's what we do at this stage. We balance all atoms excepting oxygen and hydrogen. Okay, now for the next step is where we balance the oxygens by adding water. So for the first half equation, there are 4 oxygens here, but there are none on the right side. So what I would do is add 4 water molecules on the right side. In the case of the second half equation, we have 4 oxygens here, and we have 2 times 2, 4 oxygens. So therefore, we don't need to balance the oxygens for the second half equation because it's already balanced, all right? Okay, the next step is that we balance the hydrogens by adding H plus ions to the side that needs it. So you notice that we have 8 hydrogens here. Excuse me, we have none on this side. So I'm going to add 8 hydrogen ions on the left side, all right? In the case of the second half equation, there are no hydrogens on either side, so we don't need to make any changes as far as that is concerned. Okay, so the next step is where, again, as I said before, students tend to screw this up because the next step is where we balance the charges by adding H plus ions. So if you remember, I said that the side we add the hydrogen, I'm sorry, not H plus ions, electrons. That's what I meant to say. So if you remember, I said that the side that we add the electrons to is the side that has a greater net charge. So if you look at the first half equation here, you have 8 plus charges minus 1. So the net charge on this side is plus 7. Over here, there's only the plus 2 here. So I'm just going to put plus 2 on this side. So that means that because this is higher than this, we need to add electrons to this side. And in this case, in order to reduce the plus 7 to plus 2, we're going to add 5 electrons because by adding 5 electrons, we're adding 5 negative charges to that side, which results in the reduction of the net charge on that side to plus 2, which balances with a plus 2 on this side. All right? So that's how we balance the first half equation. Now for the second half equation, you'll notice that there's a total of minus 2 on this side, and the carbon dioxide is neutral, so there's a 0. So therefore, we add electrons to the higher net charge side, which is the right side, and therefore we would add 2 electrons to that side, all right? So that's basically how we balance the charges. We add enough electrons to the side with the higher net charge so as to reduce the net charge on that side to be equal to the net charge on the other side. Okay, so the next step is another important step because remember we said, I said it at least twice already, and I'm going to say it again. In every redox reaction, the total number of electrons lost and gained must be the same, right? Now in this case here, for the reduction half reaction, we have 5 electrons here, and for the oxidation half reaction, we have 2. So the question now becomes, how do we get the number of electrons be equal? And the answer is, we multiply this half equation here by 2, and we multiply this half equation here by 5. If we multiply this half equation here by 2, we're going to end up with 10 electrons here. If you multiply this half equation here by 5, you're going to end up with 10 electrons here. But you have to remember, this 2 will multiply everything throughout this equation, and this 5 will multiply everything throughout that equation. So if I concentrate on the first half equation, multiplying right through by 2, you're going to end up with 10 electrons plus 16 hydrogen ions plus 2 MnO4 minus to give 2 Mn2 plus 8 H2O. All right? And then for the second half equation, since I'm multiplying this right through by 5, I'm going to end up with 5C2O4 2 minus to give 10 CO2 plus 10 electrons. All right? So that's what happens when you multiply the second equation by 5. So now we have the number of electrons gained and lost canceling out because they're the same. And I don't think there's anything else to cancel out, so we can just write down what is left. So after adding these two equations, you're going to end up with 16H plus 2MnO4 minus plus 5C2O4 2 minus. So that takes care of things on the left side, and then on the right side, you're going to have 2Mn2 plus, 2 plus 8H2O plus 10 CO2, all right? And that should be the final answer, of course. But again, as I said before, you should check through to make sure everything is balanced. So let's do that now. We have 16 hydrogens, 8 times 2, 16 hydrogens, so that's balanced. We have 8 plus 5 4 is 20, so that's 28 oxygens on the left side. We have 8 plus 2 10s 20, 28 oxygens on the right side, so that's okay. We have 10 carbons here, 10 carbons here, so that's okay. And as far as the manganese, we have 2 manganese here, 2 manganese, and then the charges. Let's look at the charges. We have plus 16, minus 2, minus 10. So what does that give? 16 minus 2, that's 14. 14 minus 10, that's 4. So plus 4 on this side. And here we have 2 times plus 2 plus 4. So the charges are balanced. So therefore, the equation is correct. All right. Any questions on this one? Any questions? Okay. Let's see here. All right, let's do another example. Let me clear this here. Okay. Okay. Let's start off with all right. NO3 minus plus Mn2 plus to give N2 plus MnO4 minus. Okay, so that would be, all right, you know what? Let me leave this up here since it's almost 10:50. So it's 10:48, but I don't want to start and stop in the middle of this problem. So let's take another break, and then at 11 o'clock, we will commence with this particular problem, all right? Okay, let's continue. Okay, I take it you can see my screen. So, all right, so we're going to do this example here, all right? So let's start off by the first step, which again is the separation into two half equations. So one half equation would be NO3 minus to form N2, and MN2 plus to form MnO4 minus, all right? The next step is that we balance all atoms excepting oxygen and hydrogen, which means that for the first half equation here, we need to put a 2 here to balance the nitrogens. And for the second half equation, we don't need to do anything. Okay, the next step is that we balance the oxygens by adding water where needed. So in the case of the first half equation, we have 6 oxygens on the left, and therefore that means we're going to add 6 water molecules on the right. In the case of the second half equation, we have 4 oxygens on the right, which means that we add 4 water molecules on the left. Okay, the next step is to balance the charges. So what does that mean for the first half equation? Well, that means that we have 2 negative charges here. We have no charges on this side, so that means that we need to add, oh, wait a minute. Something is not adding up here. 103. Oh, I'm sorry. We need to balance the hydrogens. So to balance the hydrogens, we add H plus here. We add 12 hydrogen ions here. And for the second half equation, we add 8 hydrogen ions here to balance the hydrogens. Then we balance the charges. So to balance the charges, we have a total of 12 plus minus 2, so that's plus 10 on this side. We have 0 on this side, so that means that we would add 10 electrons to this side. For the second half equation, we have plus 2 on this side. We have 8 minus 1, which is plus 7, which means that we need to add 5 electrons to this side. Okay, so the next step is to ensure that the number of electrons lost and gained are the same. As we have it right now, we have 10 electrons here. We have 5 electrons here, which means that I would multiply this here by 2. So when you multiply everything by 2, you're going to end up with 8 water molecules plus 2 Mn2 plus to give 2 MnO4 minus plus 16 hydrogen ions plus 10 electrons. Okay, and what I'm going to do to avoid confusion, I'm just going to cross out this right here and add this equation to this equation, which means that the 10 electrons will cancel out here and here, but some other things will cancel out. For example, we have 12 hydrogen ions here, and we have 16 here. So what will happen is that these 12 will cancel out 12 of these, leaving behind 4, all right? And we have 6 water molecules here, and we have 8 here. So what that means is that these 6 water molecules will cancel out 6 of these, leaving behind 2, all right? And then we just add up what is left. So what will be left would be the 2NO3. Oh gosh, what's going on here? 3 minus plus 2H2O plus 2Mn2 plus, and then on the right side, we're going to have N2 plus 2MnO4 minus plus 4H plus. And again, as I said before, we should check through to make sure everything is balanced, including the charges. So we have 2 nitrogens here, 2 nitrogens, so that's okay. We have 6 plus 2, 8 oxygens, 2 times 4, 8 oxygens. Then we have 4 hydrogens, 2 manganese, 2 manganese. And then as far as the charges are concerned, we have -2 plus 2 times +2, which is +4, which will give you -2. And here we have -2 plus 4. Actually, this will give you +2, my bad. So this will give you oh gosh, what's going on here? Oh, +2. And this is -2 plus 4, which will give you +2. So everything is balanced. So this would be the final answer. All right. Okay, any questions about this one? Any questions? Any questions? Okay, so let's do another one. This time, you're going to tell me what to write down. So that I'm confident that you guys will be able to solve problems of these types. So let's say you're given SO4 2- plus NO2- to give SO3 2- plus NO3-. Okay. All right, so what would be the very first step? Well, let me make sure everything is copacetic. Yeah, okay. So based on what we have done so far, based on the examples that we have looked at so far, what would be your very first step in this process? Anybody?
Making sure that each side is balanced.
Nope,
No?
that's not the first step. Before you get to that part, you need to do something.
Split them into the half equation.
Exactly. So,
Oh, yeah.
so the 1/2 equation would be SO4 2- to SO3 2-, and the other half equation would be NO2- to NO3-. Okay, very good. What would be the next step? We have to balance something in this step. We balance what?
The oxygen.
Nope.
It's not the charges yet, right?
Nope, 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 nope. You can look at the list of rules if you have it, or hold on, I don't think it, well,
I might have it. I know I have it.
hold on, let me see if I can find it.
So,
Rule number 3, what does it say? Balance the atoms other than oxygen and hydrogen, right? So that means that in this case, we look at the sulfurs, and the sulfurs are balanced, and we look at the nitrogens, and they are balanced as well. So we don't need to do anything as far as that is concerned, right? Okay, so the next step is what? After we ensure that all atoms, apart from oxygen and hydrogens, are balanced, what's the next step?
Balance the oxygens and hydrogen.
Well, okay, so let's deal with the oxygens first. How do we balance the oxygens for the first half equation? We have 4 oxygens on the left,
So you're
and
gonna
we have 3 on the right. So what do we do?
add one.
How do we add it?
Add it.
How do we add oxygens?
You gotta add one to the left side, which is gonna give you.
But what do we add? We can't just add an O like this, right? We have to add something which contains oxygen.
Electron.
Nope.
Hold on.
Let me go back to the rules here.
Hold on.
It says we add water to balance the oxygen atoms, right?
Oh, yeah.
Right. So let me go back here. So that means that in this case, let me go back to my pen. In this case, we add 1 water molecule to this side, right?
Mm-hmm.
So now we have 4 oxygens on the right, which balances with the 4 oxygens on the left. And what do we do to the second half equation? We have 2 oxygens here, we have 3 here, right? So what do we do?
You do the same thing, right?
But we have to do it on this side.
Yeah.
Okay, very good. All right. So the next step is what? After we balance the oxygens, we balance the
Charge.
hydrogens.
Oh, yeah.
And how do we balance the hydrogens? By adding?
H plus.
Exactly. So what does that mean for the first half equation? We have 2 hydrogens here. We have none on this side. So what do we do?
Add 2 H plus.
Exactly. We add 2 H plus ions on the left side. And then for the second half equation, we have 2 hydrogens here. We have none on this side. So what do we do?
Add 2 H plus ions on the right side.
2 H plus on the right side. Okay, very good. Okay, so what's the next step? We balance the what?
Charges.
And how do we balance the charges?
Charges. Is that when you add the electrons?
Exactly. So let's deal with the first half equation. To which side do we add electrons and how many?
So you got, let's see.
How many charges do we have total on the left side? We have +2, -2, so that's 0.
Mm-hmm.
And we have -2 on this side. So how many electrons would you add and to which side would you add it?
You would add 2 to the right side to make it 0?
Nope. If you add 2 to the right side, you're going to make the total charge on the right side -4.
Oh, that's right. That's right. So it's going to be on the
Left side. Exactly. All right. And then what about the second half equation? We have -1 here, and we have +1 here. So which side would you add electrons and how many?
Two to the right side.
Exactly. Okay. And it just so happens that the number of electrons gained and lost are the same. So we don't need to do anything to make sure that that happens. So all we have to do from here is add these two equations together.
Because otherwise you would have to like multiply, right?
Exactly. So yeah, so for example, if this was a 4 here, then you'd have to multiply this by 2.
Okay.
But we don't have to do that. So.
And you would just multiply the right side or the whole thing?
You multiply the entire equation. You can't just multiply the number of electrons.
If that was the case.
If that was the case, exactly. Okay, so when you add these two, the 2 electrons will go here and here, and the 2 H plus will go here, And the water molecule will disappear as well. And guess what? And I just realized this. The final equation would be the same as the first equation. The equation is already balanced. That's what happens when I create questions on the fly. I'm not particularly good at creating questions. So this was, I mean, it's a good exercise, but basically we went through all these steps for nothing.
I mean, it taught me.
Well, yeah, you learn the steps. Exactly, yeah. Okay, so let's do another example. A last one. Hopefully I'll be coming up with a better one. Okay. Suppose you are given V3 plus CrO4 2 minus to give V2O5 plus, whoops, oh gosh, plus Cr3 plus. Okay, let's look at this one. Okay, so the first step would be what?
Right, the 2 half equations.
Okay, so one half equation would be this, and the other half equation would be this, all right? Well, that's one half equation. The other one would be CrO4 2 minus to give you Cr3 plus. Okay, very good. What's the next step?
Balance the non-hydrogen or oxygen.
Okay, so what does that mean for the first half equation?
Put a 2 on the...
Here, right?
Yeah.
Yeah.
Okay, and then for the second half equation, you don't need to do anything because you have one chromium on both sides, all right?
Right.
Okay, next step. What's the next step?
Balanced oxygen.
Okay, so what does that mean for the first half equation?
You're gonna have
You have 5 oxygens here, right?
yeah.
So what do you do to balance it?
Add H2O.
Yeah, how many?
5.
5 water molecules, exactly.
Yeah.
And then for the second half equation,
You're gonna add 4 to the right side.
exactly, 4 water molecules to the right. Okay, very good. What's the next step?
I think now we do the electron.
Nope.
Nope.
You're skipping a step.
Uh-oh.
Add the hydrogen ion.
Oh yeah.
Exactly, right, hydrogens. Okay, we need to balance the hydrogens. Okay, so what does that mean for the first half equation?
You got to put 5 on the right side, right?
Nope. You have a total of 10 hydrogens here.
Oh, okay. 10.
So that means you had 10
Yeah, 10.
H plus. Right, exactly.
Got
Okay, what about the second half equation? You have 8 hydrogens here. So what do you do over here?
You're gonna add 8 hydrogens to the left side.
8 hydrogen ions. Okay, very good. Now, as I said before, students keep messing up on the charges, balancing the charges. So, how would you balance the charges for the first half equation? How many charges total do we have on the left side for the first half equation?
3.
Nope.
Hold on.
See this 2 here?
Oh yeah, 6.
Right. So plus, you see, you have to be careful, man.
Yeah.
Okay, how many charges do we have total on the right side?
Hold on. 10.
Okay, very good. All right, so the question now is, to which side and how many electrons would you add? Yeah, +6 on the left, +10 on the right.
You could add 4 to the right side.
Exactly, 4 electrons to the right side. Very good. All right, let's do the same for the second half equation. So how many charges total do we have on the left side for the second half equation?
We got 8. And then we got. Is it 0?
Nope. You have 8 plus charges here, and you have -2 here. So what's the total?
Oh, you don't multiply that. -2 and 4. Okay, so that's 6.
+6.
Yeah, that's 6.
+6. Okay. And what about this side? We have a total of +3, right? So to which side would you add electrons and how many?
3 electrons to the left side.
Exactly. All right. So what do we do next?
Got charges.
What do we do next? You remember what I said about the number of electrons lost and gained?
Multiply the equations to make them the same.
Exactly. So what would you multiply? What would you multiply this by?
3.
And what would you multiply this by?
4.
Exactly. So when you multiply this one by 3, remember now you have to multiply everything in that line. So that's 15 water molecules plus 6 V3 plus to give 3 V2O5 plus 30 H plus 12 electrons. All right. And then when you multiply this one by 4, you're going to end up with 12 electrons plus 32 H plus 4 CrO4 2 minus to give 4 Cr3 plus 16 H2O. All right. And then we add these, whoops, what did I do here? Let me erase. Okay, let me go back to this. Okay, so we're gonna add these two together. Okay, so what's gonna cancel out? Obviously, the 12 electrons here and here, right? Okay, anything else will cancel out that you can see? This is 15 water here. Anything else will cancel out?
Can you get rid of the 15 electrons or water?
Right, the 15 water molecules here will cancel out 15 of leaving behind 1, right, on the right side. Anything else will cancel out?
The 30 hydrogen ions.
Right, the 30 hydrogen ions here will cancel out 30 of these, leaving behind 2, all right? And therefore, we just write down what is left, 6 V3 plus 2 H plus 4 CrO4 2 minus to give 3 V2O5 plus 4 Cr3 plus H2O. And that should be the final answer. But of course, as I always say, make sure you check and make sure everything is balanced. So let's do that now. 6 vanadiums, 3 times 2, 6 vanadiums, so that's balanced. 2 H plus, 2 hydrogens, 4 chromiums, 4 times 4 is 16 oxygens, 3 times 5, 15 plus 1, 16 oxygens. And then the charges, we have plus 18, plus 2, minus 8. So that gives you what? 18 plus 2, that's 20 minus 8, that's 12. So that gives you plus 12 on the side. And here we have 4 times plus 3, that's plus 12. So everything is balanced. All right? Okay, any questions about this example? Any questions? Okay.
No,
Cool.
no questions. It
All
took
right.
me a couple examples to get through it though, but I got it now.
Yeah, that's the reason why I you know, based on past experience, you know, students, you know, how should I put this? The steps are straightforward,
Yeah.
right? But you know, you have to be careful.
The
If you
technicalities of the charges and then
exactly, if you make
kind of balance it.
right, if you make an error earlier in the process, it screws up everything afterwards. So, you know, you have to practice, you know, to get a better handle on how to actually do this successfully. So that's the reason why I went through all those examples. So all I can say is that the more you practice these problems, the better you become at it. If you look in your textbook, I'm quite sure you'll find more problems to do on your own so that you can become more proficient at balancing these equations. Okay, so let me skip all this here. We covered this already. Okay, some other definitions that we need to cover. Very simple, an oxidizing agent causes another substance to be oxidized while it is reduced. And the reducing agent is basically the opposite. It causes another substance to be reduced while it is being oxidized. So basically, in a redox reaction, the oxidizing agent is undergoing reduction, the reducing agent is undergoing oxidization or oxidation. And what this is showing you are some oxidation numbers of particular nonmetals based on their groups. So for example, in group 5A, nitrogen can have oxidation numbers ranging from +5 to -3, depending on, you know, the ion or molecule it's a part of, all right? In the case of group 6A elements, like sulfur, the oxidation number can range from +6 to -2. And in the case of group 7, the oxidation number can range from +7 to -1, all right? And you can determine the maximum and minimum numbers by basically this rule here. The maximum oxidation number is equal to the group number, right? Such as nitrogen +5, sulfur +6, and so on. And the minimum group number would be equal to the group number -8. So for example, in the case of group 7A, the minimum group number for any element in that group would be 7 - 8, which is -1, which is what we have here in the case of the chloride ion, all right? And it says here that the species in the middle of their oxidation number range can act as either oxidizing or reducing agent. And it all depends on what it's reacting with, all right? Okay, now let's talk about metals as a reducing agent, because metals by themselves, they tend to donate electrons in their reactions, right? And therefore they tend to be reducing agents. Now, of course, different metallic elements will have different strengths in terms of their reducing capacity. And we can arrange it in terms of the series. In some textbooks, they call it the activity series. In other textbooks, they call it the electrochemical series. It's basically the same thing. And as you can see in this series, potassium is in this list, the most powerful reducing agent, followed by calcium, followed by sodium, and so on. And we can use this as a predictive tool in terms of determining which metal atom will displace the ion, another ion from its solution, all right? And basically the rule is that a metal will displace from a solution the ions of any metal that lies below it in the series. So for example, zinc will replace the hydrogen here to form H2, all right, in this reaction. And we can predict that because of the relative position of zinc, which is here, to hydrogen, which is right here, all right? So based on these relative positions, zinc is higher than hydrogen. We know that zinc will displace hydrogen from hydrochloric acid to form zinc chloride and hydrogen gas. Now, in terms of a reaction that will not occur, if you take copper and try to react it with, let's say, sodium chloride, that reaction will not take place. Why? Because copper is below sodium in the activity series. All right. So basically, because copper is below sodium, we know that this reaction will not take place. On the other hand, if you have sodium and you add it to a solution of copper 2 chloride, then you're going to end up with sodium chloride and copper being formed. And that's because sodium is above copper in that series. So that's basically how we use the how we use the activity series to make predictions when it comes to certain displacement reactions. Okay, this is us showing you a redox, what we call redox titration. We talked about titration earlier. When it comes to acid-base reactions, we can also do what we call redox titration. In this case, I think we're looking at the reaction between the permanganate ion, which is MnO4 minus, reacting with Fe3 plus, if I remember correctly. And then the products of this reaction would be Mn2 plus and Fe2 plus. I think that's what this is. I could be wrong. In any case, I know that permanganate is the solution in the burette because it has a purple color, all right? And basically what you're doing is adding, you have your solution down here, which I think is Fe3 plus, and you're adding your permanganate solution to your Fe3 plus solution until you get a slight pink color here. And that pink color is due to the manganese 2 plus ion that is formed. So that's basically what this is all about. Unfortunately, we won't be doing this reaction in our lab course. And the main reason why is because the waste products are very expensive to get rid of. We cannot just pour the waste products down the sink for environmental reasons. And the manganese 2 plus that is produced is basically the toxic material that we have to be concerned about when it comes to the waste. And, you know, if we do this experiment, we have to actually pay a company to get rid of it. And, you know, we're trying to minimize costs in the science department. So unfortunately, we can't run that experiment. However, I'm working on another redox experiment, which I have not perfected yet. Unfortunately, we won't be doing it in this course, but for future courses, I plan to introduce it to my students. Okay. This is another redox reaction here involving the dichromate ion. I'm not sure what it's reacting with, but basically it's the same idea where the orange color, the red color, if I'm not mistaken, becomes orange for the chromium. I don't remember exactly, but that's another example of a redox reaction. Okay, so that's basically it for chapter 4. So we actually are making good progress as far as these chapters are concerned. So let me move on now to chapter 5. So let me go here. Okay, so chapter 5, we'll be dealing with gases. All right. And a lot of what we are going to cover in chapter 5, you should have met before, especially with respect to the gas laws. There are a few other things that we're going to cover, which I don't think you would have covered in high school chemistry or introductory chemistry, and that would be to the latter part of this chapter. I would say that the difference, of course, between what you learned in high school chemistry and what we're about to cover here is that the problems will be a bit more challenging, all right? But for the first half, or I would say the first 3/4 of this chapter, it's basically a review of stuff you would have learned before. All right, so let's talk about gases. What are they like? Well, we know already, you should know from before, that gases are composed of particles, molecules or atoms that are always moving in random motion, and they're highly energetic. And as a result, they impart certain properties to gases. For example, gases, they flow readily and they spread out to occupy the entire volume of their container. And very often you'll meet this term vapor, right? A vapor is basically a gas that is a liquid at room temperature and pressure. So for example, we use the term vapor with reference to water or methanol, because these substances under normal room temperature and pressure conditions exist as liquids, but when you heat them, of course, they convert to the gaseous state, so we call that the vapor. But when it comes to substances like oxygen or hydrogen that exist as gases under normal room conditions, we simply use the term gases. We don't use vapor in reference to those substances, all right? What you'll find, going back to the vapor concept, is that low molecular compounds or low molar mass molecular compounds, they exist as either gases or easily vaporizable liquids. So water is an example of that. Methanol is another example of that, all right? Now, some examples of gases are shown here. And as you can see, these gases have applications. So for example, chlorine is used as a disinfectant or bleach. Methane is a fuel, which is also used in the manufacture of hydrogen. Excuse me, propane is basically used for heating. So when you see any gas tanks with LPG label on it, that's liquid petroleum gas, it's actually propane, C3H8, all right? So those are just some examples of different common gases and their applications. Now, in order for us to understand the behavior of gases, we have to appreciate the theory behind it, which is the kinetic molecular theory. And this theory basically provides a model for the behavior of gases at the microscopic level. And then we can basically use this theory to explain the gas laws that we're going to meet later on, all right? So basically the assumptions of this theory is that, as we said before, the particles are in rapid random motion, and they move through a motion known as translational motion, which basically means that it moves in straight lines. In fact, the only way that they deviate from that straight line motion is that they come back, they collide with each other or with the walls of the container. And as a result of our understanding of this model, we can appreciate, for example, why gases exert pressure on the walls of the container that they're in. And that's because of the continuous bombardment of the particles against the walls of the container. And that collectively will manifest as the pressure that the gas will exert on the inner walls of the container. We can also relate the behavior of gases in relation to the temperature, right? Because when you increase the temperature of a gas, you're imparting kinetic energy to the particles. The particles will move faster, and therefore they will hit the walls of the container with greater hardness and more frequency, and would exert a greater pressure on the walls of the container. So that explains why, as the temperature of the gas increases, the pressure increases as well. So as you can see, the kinetic molecular theory is very useful for explaining all these things that we observe about the behavior of gases. Okay, so let's talk about the concept of gas pressure. Now, pressure is different from force. You know, people in everyday language tend to use the term pressure and force as if they mean the same thing. Well, as you can see here, by definition, pressure is the force per unit area. And you should have learned that, well, let me not say you should have learned. Well, yes, you should have learned this, that force is basically a push or pull, all right? So if you're pushing or pulling on something and that force is transmitted over a certain area, then at the same time, you're exerting pressure over that area, right? Now, the unit of force is expressed in newtons, and the unit of area, according to the SI system, is in meters squared. So therefore, the unit of pressure will be newtons per meter squared. And collectively, the name for that unit is called the Pascal unit. So whenever you see Pascal, it's the same thing as Newton per meter squared. And therefore, you can have smaller or larger units of Pascal if you use the prefixes. So for example, kilopascal, right? is basically 1,000 pascals, right? And this actually is more often used because the Pascal unit is a relatively small unit. There are some other units as well that you need to be familiar with. You have the atmosphere unit, and I'm going to explain how that unit came about. And then you have the millimeter mercury unit, which is the same thing as the torr unit, which I'm going to explain that unit as well, how we end up with the torr unit or the millimeter mercury unit, all right? Now, there's a relationship that exists between the Pascal, the kilopascal, the atmosphere, and the millimeter mercury unit, and that is given in this small chart right here. So here we have a 1 atmosphere unit, and it's equal to all of these, right? 1 atmosphere is equal to 760 millimeter mercury, which is the same thing as 760 torr, which is the same thing as all the others here. Now, let me just say that I honestly don't anticipate us using this, or this. So this is the bar unit. This is the millibar value. This is the pounds per square inch. I honestly don't anticipate that you'll be using any one of these, all right? But the others you'll definitely be encountering in this chapter. The newtons per meter squared, which is the same thing as the Pascal, and the kilopascal units, along with the millimeter mercury unit and the torr unit. So those are the units that you'll be encountering a whole lot in this chapter. Okay, so how do we measure the pressure? Well, it depends on what you're measuring. Now, if you want to measure the atmospheric pressure, right? Now, we all know that the air we breathe is a mixture of gases, mostly nitrogen, which is about almost 80% of the air we breathe. And then the next element in terms of abundance would be oxygen, and then you have some other elements, all right? So as a collection of gases, that mixture exerts pressure, right? So as we're walking around on Earth, you know, sleeping, sitting, whatever, we are actually experiencing the pressure of the atmosphere on our bodies, all right? So, you know, that value, that pressure has a value, and it can be measured using an instrument known as a barometer. So by definition, 1 atmosphere, this is where the atmosphere unit comes about. It is the pressure exerted by a column of mercury exactly 760 millimeters high. And it turns out that these are the other relationships between the atmospheric pressure and these other units. So I talked about the millimeter mercury unit a while ago. The torr unit is the same thing numerically as the millimeter unit, and the relationship between the atmosphere and the kilopascal unit is given right here. Now, the way this particular millimeter mercury unit was obtained is from this setup right here. So I'm sorry. So what you see here are 2 troughs filled with mercury. And mercury is a liquid of choice for one important reason, which I'll talk about later on. But for now, just accept that mercury is a liquid of choice that is used in these setups, all right? Now, in this trough, we have a tube where both ends are opened, all right? So basically, what will happen is that the atmospheric pressure will act on the surface on the outside of the tube as well as on the surface on the inside of the tube. So therefore, the atmospheric pressure exerted here on the outside and here on the inside on the mercury surface will be the same. So therefore, as a result, the mercury level here on the inside will be the same as the mercury level on the outside. No problem understanding that, right? Now, in the setup on the right, we have a different setup whereas one end of the tube that is used is sealed and the other end is open, right? So the way this is set up is that whoever set this up would have mercury inside the tube initially, and then they will use their thumb to cover the mouth of the tube and invert it into the trough with the mercury and then leave it to stand for a while. And what will happen if the tube is long enough, meaning more than 760 millimeters, what will happen is that the mercury level will fall until it gets to a height of 760 millimeters above the surface of the mercury on the outside of the tube. What that means basically is that this mercury column will exert a pressure at the same level inside the tube as the atmospheric pressure that is exerted on the outside of the tube. And therefore, this is where the atmospheric unit comes in, because based on this setup, it was decided that 1 atmosphere, which is the pressure exerted by the atmosphere, would be equal to 760 millimeter mercury, because that's the height of the mercury column that is supported by the atmospheric pressure. So that's where we get the atmosphere unit from, and the relationship between the atmosphere unit and the millimeter mercury unit, all right? So that's basically the simple mercury barometer. Okay. Any questions about the mercury barometer? Any questions? Any questions? Okay, so simple example. You're given the pressure in kilopascals, excuse me, and you're asked to determine the pressure expressed in torr. So remember that the relationship between the torr and the kilopascal unit is that 760 torr is equal to 101.325 kilopascals. So if you want to convert from kilopascals to torr, this is how we set this up. It's 100.2 kilopascals multiplied by 760 torr divided by 101.325 kilopascals. So let me do my number crunching here. 100.2 times 760 divided by 101.325. So according to my calculation, this works out to be 752 kilopascals. 752 kilopascals. So that's it. Relatively simple example. I don't think you would have any questions about that one. Okay, let's move on now to another instrument that is used to measure pressure, but this time pressure for gas. So let's say you have a gas in a container, then this would be the instrument that you'd use to measure it. It's called the manometer. So basically, if you look at the diagram, excuse me, for the setup of the manometer, you'll see that the way the pressure is determined is that we use the difference in the height of the mercury or other liquid, but as I said before, mercury is the liquid of choice for reasons I'm going to explain later on, in the two arms of the manometer. So let me show you on the next slide what the manometer looks like. So here is the diagram showing you what a closed end manometer looks like. And later on, in fact, I think the next slide, I'm going to show you what the open end manometer looks like. So as the name suggests, one end of this U-shaped tube is closed, right? There's a vacuum here, right? Above the mercury level here. So the pressure here is 0, all right? This end is connected to the container, which has a gas. So when you open up the tap right here, the gas flows through and exerts the pressure here, right? So there's no pressure exerted here. The pressure of the gas will be exerted on this end, and the pressure exerted by this gas would be equal to the height difference between the two mercury levels, which is given by delta H right here, all right? So that's basically how you determine the pressure of the gas in this setup, all right? So as stated here, the pressure of the gas is equal to the height difference, which is delta H, okay? Now, you can, if the liquid is mercury, express the pressure in terms of millimeters of mercury, right? However, if you're using some other liquid, or mercury for that matter, or so any other liquid, you can calculate the pressure expressed in pascals using this equation right here, right? Where G is a constant known as the acceleration due to gravity, D is the density of the gas in kilograms per meters cubed, and H would be the density, the depth of the, below the surface of the liquid. So this H would be the same thing as the delta H right here. So if you are using some other liquid, or even in the case of mercury, if you want to calculate the value in pascals, then this would be the equation that you would use to determine the pressure in pascals, all right? So that's the open end manometer. Now, that's a closed end manometer. Now, the next slide here shows you what happens in the case of the open end manometer. Now, since it's now 11:59, I'm going to stop right here and again, rest for 10 minutes, and then we're going to commence with the discussion of the open end manometer, all right? So I'll be back in the next 10 minutes. Okay, so I take it you can hear me. So let's proceed to a discussion of the open-end manometer. So as the name suggests, one end here is open to the atmosphere. The other end is connected to your container with the gas, all right? So two things you need to recognize in this particular setup. So the gas, once this tap is open, will flow through here and exert the pressure right here, right? So that will be the pressure of the gas right here. On the other hand, on this side here, because this is open to the atmospheric pressure will be acting on the surface of the mercury at this end right here. So that's what P bar represents. P bar is the atmospheric pressure or the barometric pressure. It's the same thing. So you'll notice that based on this setup here, obviously the pressure of the gas here that is exerted here would be greater than the pressure that is exerted by the atmospheric here, because the mercury level is pushed up on this end, on the right side, on the left side right here. So what that means is that the difference between these two pressure values would be represented by the difference in the mercury levels shown here, delta H. So therefore, the mathematical relationship between P gas, P bar, and delta H is that P gas is equal to P bar plus the delta H, which is given by this equation right here, all right? So that's basically how you can determine the pressure of the gas, because if you know what the barometric pressure is, then all you have to do is add to that the difference between the mercury levels, and that will give you the pressure of the gas. Now, on the right, the situation is a bit different, where the barometric pressure is greater than the pressure of the gas, and that's because the mercury level is pushed up to a higher level on the right side right here. So therefore, the mathematical relationship between, well, before I get into the mathematical relationship, based on that, we can see right here, we can therefore conclude that the barometric pressure would be greater than the pressure of the gas, and the difference between them would be delta H. So therefore, the barometric pressure will be equal to P gas plus the delta H, which is given here. And therefore, based on this, we can find the pressure of the gas by finding the difference between the barometric pressure and delta H. So that's basically how the open-end barometer works. It depends on the mercury level when you compare these two, which one is higher. The one that is higher would correspond to the lower barometric pressure or the lower pressure, depending on, you know, if it's a higher end, if the mercury is in a higher level at this end or at this end, all right? Now, here we have a question. It says for part B, what is the pressure of the gas if delta H is 100 millimeters, if delta H is 100 millimeters and the barometric pressure is 760 millimeters? Well, that's very easy because all we have to do is find P gas, which would be equal to P bar minus delta H. And all we have to do is put the numbers in. So that would be barometric pressure, which is 760 millimeters mercury, minus 100 millimeters mercury, which would be equal to 660 millimeters mercury. All right, so that's basically the answer to the question that is being asked here. Okay, now, this question here, and I'm sorry for the scribblings, I was recording a video and I did a lot of writing, but I can still use it. Let me just, okay, where's the eraser? Oh, no eraser, okay. Okay, now this question here is the question that explains why mercury is the liquid of choice when it comes to instruments such as the barometer or the manometer, all right? So the question says you're to calculate the height of a column of water, and it gives the density of water, which is 1.00 grams per cm cube. That exerts the same pressure as a column of mercury, the density of which is 13.6 grams per cm cube, 760 millimeters high, all right? Now, if you remember, this formula right here is the formula that is used to calculate the pressure that is exerted by a column of liquid, where H is a height, and D is a density, and G is a constant known as the acceleration due to gravity, all right? So what this question is asking for is the height for the mercury column, given that the water, the height of the water column that would support, that would exert the same pressure as a mercury column, which is 760 millimeters high. So the first thing I'm going to write down here is that the pressure exerted by the water column will be equal to the pressure exerted by the mercury column. Now we can write down separate equations for each of these terms. So for the water pressure, for the pressure exerted by the water, that would be height of the water column times G times the density of water. And for the mercury expression for pressure, that would be equal to the height of the mercury column times G times the density of the mercury column, all right? Now, since we have G on both sides, we can cancel that out. And remember now, the aim is to determine, the aim is to determine the height of the water column. So this is what we're trying to find, all right? So to isolate it, we divide the density of water by itself here on both sides, and we end up with the density of water here. And then all we do from here is plug the numbers in. Let me bring this up here. All we do from here is plug the numbers in. So this would be the expression for the height of the water column. So when we plug the numbers in, 760 millimeters for the mercury, the density of mercury is 13.6, and the density of water is 1.00. And when you do your number crunching, you're going to end up with this answer here, 10,300 meters. The units for this would be, let me do this here. The units for this would be meters. All right? Okay, so this is the reason why water is not used when it comes to these instruments, because if you were to use water instead of mercury in your manometer, then you will need a tube which is 10,300 millimeters high. That would be equal to, that would be equal to 10.3 meters, all right? And that would be an inconvenient piece of glassware for this purpose. And just to give an idea as to what 10.3 meters is, or what it looks like, my height is approximately 2 meters. In fact, I'm just under 2 meters tall, right? So if we were to use water instead of mercury, you need a tube which is 5 times my height, right? In other words, most rooms could not accommodate such a tube. So that's the reason why mercury is used, because of the high density of mercury, the size of the tube or the height of the tube is shorter compared to the height required if you were to use water, all right? So that's why mercury is used in instruments such as the manometer or the barometer. Okay, let's see here. Okay, so what we're going to look at is the first of a series of gas laws. And this law is Boyle's law, which describes the relationship between the pressure of a gas and its volume. So basically what this law says is that for a fixed amount of a gas at constant temperature, the volume of a gas varies inversely with its pressure. So there's an inverse relationship between the pressure and the volume of the gas. Another way of expressing it is that for a fixed amount of a gas at a constant temperature, the product of the pressure and the volume is constant, all right? So mathematically speaking, we can express it like this. PV is equal to a constant, or P initial times V initial is equal to P final times V final, or as I prefer to express it as, P1 V1 is equal to P2 V2, all right? So that's basically what Boyle's law is saying, right? So what this suggests is that if you, for example, reduce the volume of the gas, then the pressure will be doubled, provided that the temperature and the amount of gas remain fixed. All right? So that's Boyle's law. So here is a couple of graphs showing you pictorially Boyle's law, how it works. So in this graph here, the one to the left, you have a plot of pressure versus volume, all right? And you see that there's a smooth curve when that is plotted for a gas. So basically what this is suggesting is that, for example, let's say that the gas in the cylinder is at a pressure of 1 atmosphere and the volume is 4V. If you were to reduce the volume from 4V to 2V, right? In other words, if you were to halve the volume, then the pressure will be doubled from 1 atmosphere to 2 atmospheres. And if you were to halve the volume further, then the pressure will be doubled further. And that's basically how that works, right? As you double the volume, the pressure will be reduced by half. If you increase the volume, if you reduce the volume by half, the pressure will be doubled. That's basically the relationship between pressure and volume. Now, the graph over here is a different plot where you're plotting 1 over the pressure versus volume. Now, if you think about it, let me do it here. If PV is equal to a constant, that means that V would be equal to a constant times 1 over P, all right? Or another way of stating it, 1 over P is equal to 1 over a constant times V, which is the same thing as a new constant K prime V, right? So basically, let me write here 1 over P here. So basically, if you plot this on the y-axis and the V on the x-axis, then the slope, you get a straight line slope, which would be equal to K or K prime. So that's why we have a straight line right here. When you plot 1 over P versus V, you're going to end up with a straight line curve, all right? Or a straight line, I should say, all right? So that's basically another way of showing Boyle's law, how it works, all right? Okay, so here is an example, a Boyle's law example. It says a party balloon has a volume of 4.50 liters at sea level, where the atmospheric pressure is 748 torr. And it says that if you take that same balloon to a height, a mountain resort, 2,500 meters, where the atmospheric pressure is 557 torr. So the question is asking, what is the volume? So again, this is one of those word problems where you have to identify, you know, what the different terms are. Now remember, Boyle's law says that P1, V1 is equal to P2, V2. All right, so 4.50 liters would be V1, the 748 torr, would be P1, and the 557 torr would be P2. So basically we can rearrange this equation here to get an expression for P2. P2 is equal to P1, V1 over V2. And all we have to do is plug the numbers in. So P1 is equal to 748 torr times V1, which is 4.50 liters, divided by V2. I'm sorry, this should be V2 here, and this should be P2. So divide by P2, which is 557 torr. The torr units will cancel out here and here. So when we do that, 748 times 4.5 divided by 557. So according to my calculations, this works out to be equal to 6.04 liters. So that's basically how that works out. All right. Okay, any questions about this example? Any questions? Okay, the next law, and this may be the final law that we'll be looking at today, is Charles' law. And this law describes the relationship between the volume of a gas and its temperature. And in words, this is the law. The volume of a fixed amount of gas at a constant pressure is directly proportional to its Kelvin. And this is very important, to its Kelvin or absolute temperature. All right. And this brings us to the concept of absolute zero, which is the temperature obtained by the extrapolation of the plot given by Charles' law to zero volume. And this represents a temperature at which the gas molecules have no kinetic energy whatsoever, all right? Now, absolute zero on the Kelvin scale is equal to minus 273.15 degrees Celsius. We get that from plotting volume versus temperature, where the volume could be in any units, but the temperature would be in Celsius, all right? So therefore, it's based on that that we end up with the Kelvin scale, where 0 Kelvin is equal to minus 273.15 degrees Celsius. So this is showing you the plot. So what we're showing you here is a plot of volume versus the temperature in degrees Celsius. Now, of course, above a certain temperature, the gas will exist as a gas. But when the temperature is lowered, then of course it becomes a liquid, and therefore there are no more volume points to plot versus temperature. So what was done was that this line was extrapolated just as if the gas existed as a gas at low temperature to see where it would cut the x-axis. And it turns out that it cuts the x-axis right here at minus 273. Write it down here. So this here would be minus 273.15 degrees Celsius, all right? So, you know, what the powers that be decided was that the new temperature scale would be such that this now would be the same thing as 0 Kelvin. In other words, basically you're moving the y-axis here over to where this is, so you end up with this right here, right? And you end up with the new temperature scale where this now is 0 Kelvin, all right? And as stated before, 0 Kelvin represents a theoretical point where the temperature, I'm sorry, not temperature, where the kinetic energy of the particles would be 0. And therefore, basically, the particles will collapse into one, I would say, unit or singularity or whatever. So therefore, there'll be no rotational motion, there'll be no vibrational motion, no translational motion that would be exhibited by the gas particles at that temperature, all right? Okay, okay, so based on what we have covered here, let's look at this particular example. It says that a balloon will have a volume of 2.0 liters where the temperature is 27 degrees Celsius. So, oh, by the way, before I forget, there's something I should have mentioned. In fact, let me mention it here. Mathematically speaking, the law would be this: V1 over T1 is equal to V2 over T2, all right? Now, V1 and V2 can be any units, in any units, as long as the units are the same, all right? But T1 and T2 must be in Kelvin. All right, so units must be Kelvin units. All right, very important. And to convert from Celsius to Kelvin, all we have to do is add 273 to the value in Celsius to get to the Kelvin value, all right? So that's important because here the temperature is given in Celsius. So if we add 273 to 27, 273 plus 27, that gives you 300 Kelvin. So here you're gonna have 300 Kelvin. The initial volume here is V1, and the final volume V2 is minus 23. So we add 273 minus 23, that gives you 250. So V2, I'm sorry, T2 would be equal to 250 Kelvin. So basically to find V2 is going to be equal to V1 over T1 times T2. And then we put the numbers in. V1 is 2.00 liters times T2, which is 273, what am I saying? 300 Kelvin, all divided by T1, which is 250 Kelvin. 250 Kelvin. Okay, so 2 times 300 equals that divided by 250. So the answer I got is 2.4 liters. In fact, to be more precise, 2.40 liters. So that's basically how that is done. All right, so that's how we do this example. Any questions about this one? Any questions? All right, so let's see what's up next. Okay, this is going to be the last thing we're going to discuss, and then I'm going to call it a day. Avogadro's law, the third law in this series, which talks about the relationship between the mole and the volume of a gas. Let me get out of this here. No. Okay, so in words, this law says that at a fixed temperature and pressure, the volume of a gas is directly proportional to the number of moles or the number of molecules of the gas. So one way of expressing it is this way: the volume is directly proportional to the number of moles, or the volume is equal to a constant times the number of moles, or the volume divided by the number of moles is equal to a constant, or another way of stating it, which is more mathematically convenient when it comes to problem solving exercises. Let me squeeze it in down here. Okay, what's going on here? Okay, V1 over N1 is equal to V2 over N2. All right, so this here is a mathematical expression of Avogadro's law. All right, now some things we need to talk about here, some definitions. STP, I'm quite sure you have met this before, stands for standard temperature and pressure, right? And the values are given as 0 degrees Celsius for standard temperature and 1 atmosphere. And this is necessary because, you know, gases, of course, their properties change with temperature and pressure. So if you want to make meaningful comparisons between different gases, then it's useful for us to adopt certain standards. And on the basis of those standards, we can make, you know, different comparisons between gases. So IUPAC decided that standard temperature would be 0 degrees Celsius and standard pressure would be 1 atmosphere. Arising from that, there's another definition known as the molar volume, right? The molar volume of a gas, by definition, is the volume occupied by 1 mole of the gas. And it is found that we can actually prove this mathematically, that under STP conditions, the molar volume of an ideal gas is equal to 22.4 liters. So for every mole of an ideal gas, if the temperature are, if the conditions are STP conditions, then we know that the molar volume, or the volume occupied by 1 mole of the gas, would be equal to 22.4 liters. All right? Okay, so that's as far as Avogadro's law is concerned. Now, based on that law, we can do this particular question. So the question says, calculate the volume occupied by 4.11 kilograms of methane. So we're going to start off with, at STP, very important. Can't neglect that, all right? So what I would do is start off with the 4.11 kilograms of methane, CH4, and try to find out the volume in liters of methane under STP conditions, all right? So we start off with the 4.11 kilograms of CH4. And what I would do firstly is convert that to grams. And we all know that 1 kilogram of methane is equal to 1,000 grams of the same. All right? And then the next step is we convert from grams of methane to moles of methane. So 1 mole of methane up here. And if you were to calculate the molar mass of methane, is going to be equal to 16.04 grams. You get that by adding up the molar masses of all the elements in the formula here. So far, these units will cancel out and you'll be left with the moles of methane. But remember, the question is not asking for the moles of methane. The question is asking for the volume in liters at STP. And if you remember, we just said that 1 mole of any gas will have a volume of 22.4 liters, and we can represent that here. So 1 mole of methane will go down here, and up here you're going to have the molar volume under STP conditions, 22.4 liters of methane above. So that this will cancel out with this, and then all you have to do is your number crunching. So 4.11 times 1,000 equals that divided by 16.04 times 22.4. And when this is rounded off to 3 sig figs, according to my answer, this is going to be equal to 5.74 times 10 to the 3 liters of methane. And that's how that is done. Okay, any questions about this example? Any questions? Any questions? Okay, all right, I'm going to stop here for today. So by way of announcements, let me do this here. So you would have noticed, I'm sure, that I've posted your assignment scores in Canvas. I am planning on sending you the graded work by tomorrow, all right? Because that what I'll be sending you would be what I've graded for assignments 4 through 11, all right? So you're going to need that because, of course, of your upcoming test, which I'm going to post tomorrow as well. You're going to need that to review for your test, right? So I'm going to post that test tomorrow. I will give a deadline date as Monday for you to complete it. And also, I'm going to, right now, go to Canvas and publish the assignments for chapter 3. So let me go here. Let me, okay, so let me see here for chapter 3. Okay. You have assignments 12 through 19. So I'm going to publish those now. And I'm going to publish as well the assignments for chapter 4. All right. I'm going to make the deadline date for those to be next week, Wednesday. So let me, oh. Okay, so I've just published, let's see here. Okay, so I just published the assignments for chapter 3. I'm going to do the same for chapter 4, right? So those will be due on Wednesday of next week, all right? And I think that's all I have by way of announcements. Any questions you guys have? Any questions?
No.
No? All right, so that's it for today. So
how many assignments are in chapter 4?
I'm sorry?
How many assignments are in chapter 4?
Let me see. 20, 21, and 22. Three assignments. Oh, so I just published it. Okay, hold on. Yeah, so I just published it. Right. So
right.
They're all published.
I saw that chapter 3 had 8 assignments done. I was like, oh no, and we have the 4th chapter as well.
Yeah. Yep, that's how it is. All right. Any other questions? Okay, if there are no other questions, that's it. Enjoy the rest of your day. And I guess I'll see a couple of you in the lab later on today. All right.
And of course, as far as I remember, we do not have class next Monday because it's the 31st, Memorial Day.
Thanks for reminding me. That means I will extend the deadline for that test to Tuesday then. So thanks for reminding me of that.
Yep.
Yeah, no class. There's no class next week, Monday. No class. I'm quite sure you need a break, and I certainly do. All right. So enjoy your weekend, the holiday weekend, and I'll see you guys next week, Wednesday.
Yep.
All right. Take care.
See you in the lab.
Yes, sir.